Welcome everyone. This is Qualmark's Ask the Experts presentation. Qualmark is the leader in accelerated stress test technology, and we invite you to visit us online at www.qualmark.com to learn more about HALT and HAS and the many products and services we offer. I'm Gail Eckert, and I'm the Director of Marketing for Qualmark and will be the moderator of today's event. I'd like to thank you all for taking time out of your busy day to attend. Today, Kirk Gray will be presenting New Concepts in HALT Testing, Reliability Test Plan B, which proposes a new approach to electronics reliability development, moving away from the legacy of Military Handbook 217. Kirk Gray is a consultant with over 32 years in the electronics manufacturing industry, the last 7 as a senior reliability validation engineer at Dell Inc. There he created, wrote, and implemented the HALT to HASA development process on PSUs that became a standard for all Dell PSU suppliers and was actually recognized for being the highest return on investment for the company. Welcome, Kirk.
Thank you, Gail. Welcome all. Hope everybody had a great summer. Thanks to Gail and Qualmark for allowing me to present this webinar to you today. And thanks to all of you for attending. I want to go over a little brief presentation summary. We're going to go back and talk about a little bit about how reliability engineering developed, the traditional reliability engineering, which we'll refer to as Plan A. And then we'll talk some details of Plan B, basically, the new paradigm in reliability testing and testing to empirical limits. We want to use and base it on the stress strength concepts. We'll do a brief history, case history at Advanced Energy Industries, and talk about some conceptual advanced applications of HALT, including boundary maps and other things we can do once we've reached and found limits. And we'll be happy to answer your questions at the end. I want to start off today a little humor. I felt Scott Adams almost made this cartoon strip for me. Unfortunately, in today's world, this is in reliability, traditional reliability engineering, this is a very relevant cartoon. Still, a lot of pointy-headed bosses and management still want to use the old traditional reliability methods were based on fundamentally flawed assumptions. But of course, after all, who's going to come back 3 years after your prediction and prove you wrong? And they really didn't care too much, and still many don't care how valid or invalid they are. So looking at the traditional reliability or reliability Plan A was somewhat of an absolute-based, absolute in the fact that we talk about the absolute life in components. The testing was the foundation of traditional reliability, and it was built upon adding up fit rates, and calculating all the fit rates of components, and then coming up with an MTBF level. Components failing it continuously throughout the life of the product was one of the assumptions. And of course, the dominant stress was high temperature, even though few common failure mechanisms were dependent on temperature only. Reliability tests were based basically on the worst case conditions that might be in the end-use environment, plus maybe some margin. There was a belief that the life of the components could be calculated, and therefore test equivalence of life acceleration of the components and therefore of the system could be calculated. Of course, the pros and cons of traditional reliability testing. The pros, for the most part, the system would pass, and of course, during product development, that's a good thing in some cases. But this leaves a lot of questions regarding the reliability risk that the product may have. It's also not using the full stress capabilities as most of us in this field of HALT realize once you start testing to limits, you find most systems have much more margin than the designers ever expected. Low margins, of course, would be possibly discovered later in mass production, hopefully not at your customer site. It leads to thinking that the elevated temperature is the best burn-in, best stress for accelerating failure mechanisms. And that, of course, resulted in the traditional burn-in process. And the worst thing is that you're leaving test capital from the additional stress margin capability. Testing capability capital is being left on the table. So looking at the alternative in the new paradigm, reliability testing plan B is really based on empirical operational boundaries and limits. The first step, of course, is to build good prototypes using design rules and lessons learned. Use HALT to find the margins. If they're not at the fundamental limit, then improve those margins within the cost constraints. And then that would lead to a robust product that you can develop an effective HAS or HACCP process on. Just a word about terminology before we move further. One of the terms we use, and it's used quite widely in our testing, is failure. And that's a fairly negative connotation. But there would be, and we really want to talk about limits. Of course, we know HALT and HACCP. HALT does not have failure. It just has limits. And you might consider a failure a success, especially a failure to operate when the product has a very wide margin. That would be a success if the product had a wide margin on first pass. So what do you do before you have the prototypes? Well, you plan for your testing and assemble all the test equipment required. So the benefits of reliability plan B, of course, are that it's the fastest method for finding the design weaknesses that could impact reliability. Operational margins can be used with the highest rate of stresses to validate reliability. Many believe that the stresses, the cons are potential lack of correlations or weaknesses in in-use environment. Many believe that the weaknesses found at high stress conditions are irrelevant. And this leads to a lack of investigation in what is found in the limit test. And therefore, the lack of ability to correlate it and find out if it is relevant or not. There is a higher risk, of course, catastrophic damage to the sample under test, but this mostly occurs in the HALT, in the vibration aspect of HALT. My experience in 20 years is it's very, very difficult with thermal limits or thermal stress to destroy, especially digital electronics, or cause catastrophic failure, because the thermal limits, usually the operational limits, come well before the destruct limits. Especially in cold, it's very rare. As most systems will fail their signal integrity and cause an operational failure before destruct. Just to go back and understand a little bit of how it became this way, we look at the history of reliability electronics. Back in the tubes days, of course, thermal issues were dominant. The hotter the filaments and tubes, the faster the tube would leak and the filament would burn up. This thinking kind of carried through to the early days of solid-state electronics, where there were very few electronic manufacturers and methodologies. And thermal stresses may have been more of a dominant factor. MIL 217 would have had some correlations to real-world failures. Of course, MIL Handbook 217 hasn't been published in 15 years. So MIL Handbook 17, of course, was the Bible of electronic reliability prediction, and therefore the foundation of reliability engineering. It's been removed as a reference for government contractors, and so many important relevant factors were not considered in MIL Handbook 217. Most of the data was way out of date, and the data was not based on engineering knowledge or material science knowledge. Temperature was the main factor causing failures, and it was misapplied to most failure mechanisms. That's why some people like to refer to the erroneous equation, as it was erroneous for most failure mechanisms. It's still perceived, unfortunately, the generally accepted industry standard methodology, and of course it's, even though it hasn't been published in 15 years, it's still the basis of many current reliability prediction applications, including Telcordia 332 and a lot of the other progeny that came from 217. It's important to realize why reliability engineering in Plan A hasn't changed much in the decades past. Reliability engineering is one of the toughest fields to release data in. The data is some of the most sensitive and carefully guarded for most companies. We all need data to get smarter, but the barriers in our litigious society and the competitive world of business, this is not going to happen. It's just not going to happen. It's also very difficult to prove the long life of electronic components and systems, as it may be 10 or more years, and not many people are going to go back and analyze, or companies are going to analyze a product that's 10 years old. The rapid evolution of technology, the changes in materials and processes also make it difficult to reference older designs. One of the, of course, many people have heard about the Microsoft's Xbox Red Ring of Death. If we could all discuss that openly and find out the real causes, we might get better at smarter would certainly help us get smarter at testing reliability. So there's a new foundation for reliability, and that's based on the stress-strength relationship. It's comparing the two distributions of stress and strength. Here's a classic diagram that's used to explain this relationship. It's basically a simple idea that where if the stress is less than the strength of the product, no failures will occur. It's where the stress starts to equal the strength that failures occur. And this can be true for bridges, from anything from bridges to an electronic assembly. And it's not only mechanical strength, but you might consider electrical strength also, or electrical signal capability. Of course, in this diagram, we don't have straight lines, we have a distribution. We might have, an example would be, for instance, a piece of portable electronics such as a VGA projector or something like that. We might, in manufacturing, have a projector is built on a Friday, would be in the low strength area, and that projector might end up being attached to a ceiling in a conference room in a low fatigue environment, and all of its life is just stationary. Another projector might be built in a different distribution of strength and would end up in the as a road part of a road warrior's tools, in the fact that he would be traveling a lot and throwing it into the overhead bins, carrying it a lot, dropping it occasionally, and this would be a high fatigue area. We can't know from the beginning when we manufacture of which side and what the life cycle stresses any individual unit can be subjected to. The strength distributions hopefully come from your controlled by your SPC processes, statistical process control, to keep this variation as a minimal. Of course, in your end-use environment, you generally don't have any control of, regardless of your specs. So as the fatigue damage starts to accumulate, the load PDF spreads out and starts to shift right. The field failures start to come when the two curves or PDFs start to overlap, where the weakest units are subjected to the highest life cycle environment. So one of the most relevant and significant change in the approach to optimizing reliability is using the full range and capability until the inherent technology limit is reached. So what you find here, and in fact, there's a great quote from the movie Apollo 13 when the actor Ed Harris said, "I don't care about what anything was designed to do. I care about what it can do." And that's really what the HALT process is about. It's moving it out, finding what it can do, and not concerned with the stress, the end-use environment. Because, again, you'll find that most products have much more strength than ever will be needed. So again, many people think that this destroys, each one of these samples has to be a new one from the beginning. And in my experience is that you can use, especially the units for thermal HALT, can be reused several times with consideration of what may have been damaged if there is a sensitive component or something that would be affected by the thermal conditions. But for the most part, I've used samples repeatedly without a significant change, especially if we just find an operating limit. So to build the maximum tolerance for manufacturing variation, including parametric variation, you want to build out to the limits of technology. What you're doing is, of course, using what wouldn't be used here in the stress range that you can use to further improve the product. Some technologies do have an inherent limit, a technological limit. For instance, an LCD. The display of an LCD function cannot work past about 70 degrees C. Now, that's an inherent limitation that we can't do much about. So in that case, if you have an LCD screen, you can either isolate it or remove it from the environment, in the stress environment. Lithium-ion batteries are, of course, another technological limit that can't be changed. But I've seen, in my 20 years experience, I've seen quite a few very small changes make large gains. In one particular, a single diode was changed from an 1/8 watt to a 1/4 watt, and that gained, allowed the system to gain 30 degrees C thermal margin. So small changes usually it only takes a small change, the weakest link, to make a very large gain in margin. It's a simple test iterative process, simple in principle, but very challenging in practice. Tolerance in the product is a key. Tolerance for manufacturing variation as well as in-use stress variations, which we have no control over. Okay, looking at that, we maximize, build in the PDF, build in the margin so the PDF distributions in operational strength exceeds the environmental stress by large margins, that the overlap of these two is very unlikely. So minimize failures by maximizing the strength. And once you start doing that, you set a whole new benchmark in your mind of what electronics are capable of. There are several other benefits of increasing this margin. For instance, once you have a large margin of product, you can develop very efficient HAS processes by using that large margin. The larger the margin, the larger the thermal cycles you can make, and the fewer thermal cycles you'll have to make, as well as vibration. For mechanical strength improvements, you also improve and can reduce the amount of packing materials required in shipping. You can use less protection materials, and maybe possibly, as you see in some advertisements, a portable computer could actually be shipped in a brown paper envelope if it was robust enough. I want to illustrate a little bit of a case study here. Back in the mid-90s, Accelero Advanced Energy Industries was one of my first consulting clients as I was doing business under Accelero Engineering. Because of the advanced energy makes very high energy power supplies that are used for thin film deposition. The downtime for one of their systems in a fabrication facility can be quite high, so it can be was quite painful for them to have failures at the field. This work was done in actually 1995, but Advanced Energy had such a success with it, they did not allow me to come back until 2000, 5 years later, as they realized after that period of time that how difficult this concept and this change in concepts of reliability was for many of the companies that they actually had purchased and tried to introduce it into. So they weren't as concerned about this being a competitive process or their competitors would pick up on. So the first product we decided to apply HALT and HAS to was a product that had been shipping some period of time, I think of maybe a year or so. It was a 6 kilowatt, and also there was a 12 kilowatt power supply that was in the same chassis size and function. They all had a 4-day burn-in process, which was a significant cost for them in electrical power because of these high energy power supplies. And by the way, the end-use environment was a clean room or a clean room chase, and it was very, very benign. And this, of course, leads to the concept or the fact that the product may never see these vibration or combined environments in an in-use environment, but it is valid if it finds latent defects, regardless of the product never seeing it. Here's an actual photo of the power supply. Underneath these panels here was the 100 amp, 500 volt bipolar switch, and that ended up being the weak link in the product. We did thermocouple around the switch. We also looked at the parametric characteristics of the signals going into the switch, and that was monitored continuously as we investigated the cause of this weak link. And I really appreciated Advanced Energy allowing me to take these photographs and present this in the year 2000. So looking at our first pass of the HALT test with the 100 amp switch, you see a level, the first failed at 60, we had another one fail at 75, and in fact another unit failed at 90 degrees C. You see that there's quite a spread in temperature limits, and of course that would be a concern in a wide PDF. So that would be, any wide distribution of these limits would be concerned that the basic distribution could easily fall into somewhere in the usable range or the specification range, which was, I believe, 35C for this product. So removing that 100 amp switch, unfortunately a 150 amp switch was the same package configuration. We reran the HALT test, and you see in our second iteration of the HALT test, we had with the new improved margins, we had significant change in the average failure point, and one of them exceeded 110C. But it's also the fact that all these started to be grouped together, showing that we had pushed that distribution much closer together. So now you see the results, and what we did, we basically shifted by switching that one component, which probably was about a $30 difference for cost from the 100 amp to the 150 amp. We increased the mean, even though this is a very small sample size, 23C. We basically also thinned up made narrower the PDF distribution, which of course was another benefit. I believe the worst case condition for the power supply, I think it had a 35-degree spec, but I'm sure it ran up to that 50. The unit already had a very good low operating temperature, I think of -10 to -30. I'm not sure what it was. I don't recall. But and vibration halt showed that there were really no need for any changes. So the results speak for themselves. We developed a HAS process immediately after making the changes to the design, and we changed a very expensive 4 days of burn-in to only 40-minute HAS. I think it was 4 cycles, thermal cycles, and vibration, and it changed the warranty return from 5% to 0.5%. Needless to say, that is when Advanced Energy asked me not to discuss this outside. So, and I didn't for the next 5 years. We weren't able to isolate the percentage of benefit coming from the change in design versus the change in HASA, because we were basically on a path from HALT to HAS, and didn't stop and wait to see what one effect would, what the change in design was going to provide in benefit. And just a conceptual idea that I've learned over these years, one of the benefits of thermal HALT is definitely in the fact that you can do some shifting of the signal integrity, especially in digital systems. Marginal signal integrity may result, of course, in intermittent or unstable function, and it's really difficult to find, especially when it's intermittent. And this can be come from lot to lot assembly variations. Once you start to have a change in the board impedance or other parametrics, you may have a marginal condition get much worse. And these are very, very difficult to find in failure analysis. A lot of times they're dependent on the system they were in, the marginal system they were in, say a component or a circuit board, and of course it's taken out individually as a circuit board and shipped back. May not be with the system it was running in, and of course it's going to be put in a golden system, and it's very likely to be C and D in FA without some additional stress or some additional skewing of parameters. So we know that signal propagation can be, in semiconductors, can be shifted or skewed through thermal stress. High temperature, we have a lower speed. Low temperature, generally have a higher speed. So we're able to change and shift, skew a little bit the signal propagation in semiconductors, and we may help simulate the timing of parametric shifts throughout the production life and through the product's life, which there may be some parametric drift in a certain component, and of course that will it may end up causing intermittent or absolute failure in time. We talk about thinking out of the box, and here's a literal example of thinking out of the box. Traditional testing tests to the idea was to test to some limited boundary. This is for temperature and voltage would be a four-corner test. With a little bit of margin might be added again to help to say protect or find out there's a little bit of margin. But by testing to actual empirical boundaries, we might be able to identify a very low margin that could actually start to encroach into the normal use operating ranges and the extremes of the operating ranges. So starting to look at the idea of building in stress boundary maps. This can be at first a single dimension. Now adding two or more stresses together, we start to get a two-dimensional map. And as you can see here, with just one sample, we'll have a nice fine line for one sample. As we start to use multiple samples and overlay those empirical boundary maps that we've developed, we start to see variation in those boundaries, some being wide and some staying thin. And this is going to, of course, show you the same type of distribution as the PDF, as we see in this next diagram. As you overlay more and more of these boundaries, and and of course dependent on how many samples you have to use, you start to see again a probability cloud or PDF starts to develop. And this really is again the stress strength diagram, here being your reliability margin between the two. So to ensure that reliability margins, once you develop it, it's very important, and it has been my experience that much of unreliability comes from the variation in production, excursions, overlooked incorrect processes, or a process that went out of control and nobody realized it. So what you want to do in the HACCP process, of course, is to sustain these margins throughout the time. And this cloud, of course, the probability cloud, is very dynamic. That margin will change as second source components are brought in. And maybe one component is discontinued and a replacement component is put in. It's very important that those components still produce the same operational margin. Just want to mention or show one of the very few pieces of real data that was produced and is publicly released, and this is a chart by from Ed Kaiser, Dr. Ed Kaiser at Cisco Systems, produced and presented at the workshop on accelerated stress test in Montreal, I think in 2002. And he shows here a comparison of the operating margin in some Cisco line cards with the normalized RMA, or warranty return rate. And of course it's not a direct relationship, but he put a best fitting curve, as you see here, the equation, showing the relationship of the margin versus the return rate. When you have this, you can actually start to make a business case for margin increases. Say you might have a 10-cent cost, then a 10-cent cost in changing a temperature range from 30 to 40 cents by increasing the level of component, wattage of component. Well, you can then determine what your estimated return or reduction in warranty rates will be, and of course that's a known monetary quantity that you can then compare with your cost of production or the cost of the design change. And there'll be several stresses you could start to key off of. Certainly voltage and thermal are one. Frequency, especially in digital systems, frequency could be another, increasing frequency. It has to be careful, of course, that the rate of return is only for the mechanical aspect. For instance, you'd want to, if you were comparing the drop height of a cell phone to our stress level, mechanical stress level, you'd want to compare that with field returns that have been returned for mechanical failure, or not, for instance, those have been submerged in water, for instance. And I believe this relationship would hold for a vibration, say multi-axis vibration, versus field mechanical reliability and returns of units. Certainly with more robust mechanicals, it would result in lower return rates. And that's the end of the bulk of my talk. I'd like to say that also you don't have to go through this new paradigm and testing jungle without a guide. We can help you. Accelerated Reliability Solutions can help you with the new school of testing, helping you guide you through the very challenged approach from many traditional engineering segments. We can save you a lot of frustration, and after 20 years of doing HALT in the telecommunications, biomedical, and computer industry, can plan and foresee a lot of the issues that will be challenged by some of the traditional reliability organizations. And here's a very relevant quote: especially in the rapid pace of changing electronic manufacturing processes. It's not the strongest, it wasn't the smartest, but it was the one that was the most responsive to change. And boy, we need change in this industry to capitalize on the amazing, really the incredible strength and inherent life of most electronic components.
Again, I'd like to thank everyone for your continued interest in Qualmark's Ask the Expert series. We host these free webinars periodically throughout the year. If you have a case study or information you'd like to share, please let me know at events@qualmark.com. I'd like to encourage you to touch base with Kirk. We have his website listed here on this slide, www.acceleratedreliabilitysolutions.com, and his email is straightforward, kirk@acceleratedreliabilitysolutions.com. So I thank everyone in attendance today, and I look forward to seeing you for our next Ask the Experts webinar.